Okay, so we ended the last video with this practice question to test if you understood the overall purpose of drug metabolism. So this is a relatively straightforward question, just to make sure you understand the overall concept. So drug metabolism is all about making compounds that are readily excretable. So we can eliminate B and C because it's talking about reabsorption, which is a concept you will revisit in pharmacokinetics. But right now, we know that metabolism is focused on taking a non-excretable drug and converting it into an excretable drug. And so A and D are potential correct answers. And then after that, we know that we're trying to create a more hydrophilic compound as opposed to a more lipophilic compound. A more lipophilic compound would actually lead to reabsorption, but we're focused on drug metabolism, which is all about making more polar, hydrophilic, ionized compounds that are readily excretable. So that all goes back to this. We're going from nonpolar to polar to allow for excretion. And in the last video, we introduced phase 1 and phase 2 reactions. And we said that phase 1 reactions can be, metabolism reactions can be broken down into 3 subcategories: oxidation, reduction, and hydrolysis. And then for oxidation, we have these CYP450 mediated reactions, and that's all of these here in pink, these 6 reactions. And we also made a note about how with nitrogen, it's more common to have N-dealkylation as opposed to N-oxidation, so that's why N-dealkylation is highlighted. And then with sulfur, S-oxidation is actually more common than S-dealkylation. And we'll see all of these reactions through a series of practice problems that I'll be showing you guys. And through those practice problems, we will cover all of these different phase 1 reactions. But we also mentioned phase 1 reactions also for oxidation, because these are all under oxidation right now. Under oxidation, there is alcohol and aldehyde dehydrogenation, which is mediated by enzymes that are not CYP450 enzymes. And I'll talk about that in a second. So keep that in mind. And then there's something called oxidative deamination, which you'll learn in a later PBT course if you haven't learned it already. And then phase 2 are all conjugation reactions. That's what they have in common. So there's glucuronidation, sulfation, glycine conjugation, and these ones right here. And again, we'll visit most of these reactions through practice problems. And something to keep in mind is a lot of times phase 1 reactions will provide or pave the way for a phase 2 reaction. So for example, I could have in my structure, this is something really common you'll see, an aromatic ring, and then I'll do a phase 1 reaction where I do aromatic hydroxylation, which means that to this benzene ring, I'm going to add on a hydroxyl group. Now this hydroxyl group can then lead to a series of phase 2 reactions. So keep that in mind, that phase 1 reactions can pave the way for phase 2 reactions. I'm going to emphasize that in a lot of the upcoming videos. So you always want to consider phase 1 reactions before you consider phase 2. But keep in mind what we mentioned in a previous video. Phase 1 does not have to always come before phase 2. Some drugs can skip phase 1. They can go straight to phase 2, or maybe they don't need phase 1 or phase 2. They're already readily excretable because of their chemical structure. They're already hydrophilic and ready to be excreted. So the point is, it's not always phase 1 and phase 2 for every single drug molecule, but in most of the practice problems, you'll see that phase 1 can allow, after you complete a phase 1 reaction, you can then see how different phase 2 reactions can come after that. And I wanted, since we're talking about oxidation in all of these reactions here, the CYP450 mediated reactions, we have these 6. These are all under the umbrella of oxidation. So I wanted to make sure we are all on the same page on what oxidation is. So oxidation is either an increase in the number of oxygens, so like a gain of oxygen, or it's a loss of hydrogen. So to understand that, we can look at three simple structures: an alcohol, an aldehyde, and a carboxylic acid. So looking at all of these reactions, an alcohol is the lowest oxidation, has the lowest oxidation state out of all three of these. And then going this way, you are actually increasing the oxidation state. And the reason for that is here, if you focus on your oxygen in the alcohol, this oxygen, right? So this carbon right here is only bonded to one oxygen, or a single bonded to one oxygen. But here, that same carbon has a double bond to oxygen. So you can almost think of it as two oxygens. And so that's more oxidized. And here you have even more oxidation because that same carbon is not only double bonded to an oxygen, so kind of like two oxygens, it's also single bonded to this oxygen. So we have a total of three, I guess, oxygens. But the point is we're either gaining oxygen or losing hydrogen. So you might be wondering, okay, well, I can see how we're gaining oxygen, but how are we losing hydrogen? Well, this carbon, if you remember from OChem, there's two hydrogens right here. So we started off with two hydrogens, but those two hydrogens now are not in the second structure because it's double bonded to an oxygen. If I had any more hydrogens, I would violate carbon only having 4 bonds. And then same thing with this third structure right here. I can't add any hydrogens here. There are no hydrogens on this central carbon. So you can see that going from left to right, from the alcohol to the aldehyde to the carboxylic acid, there's an oxygen right here, just to be clear, we are gaining oxygen or losing hydrogen. We're increasing the oxidation state. So that's the concept of oxidation. And that can help us learn these reactions over here, the alcohol aldehyde dehydrogenation reactions. So to go from an alcohol to an aldehyde, that is mediated by an alcohol dehydrogenase. So that makes sense now. It's an alcohol dehydrogenase. It's a loss of hydrogens. So that enzyme, alcohol dehydrogenase, is what's responsible for the loss of hydrogens and the gain of oxygen, right? And overall, we can take this a step further, and then we can do an aldehyde dehydrogenase. And the aldehyde dehydrogenase is responsible for taking the substrate, which is aldehyde, and converting it into a carboxylic acid. And so again, we're increasing the oxidation state. Now the actual reaction of how, and the curved arrow mechanisms of how to go throughout from structure 1 to 2 to 3 is a lot more complex, but what we have to focus on is just being able to recognize oxidation, right? So it may not necessarily be that these two hydrogens were lost and replaced with this oxygen. That goes more into OChem. That's not our focus right now. Our focus is to see the overall concept of oxidation and being able to recognize that going from an alcohol to an aldehyde to a carboxylic acid, you're increasing your oxidation state. Conversely, if you go from an aldehyde to a alcohol, so for example, if you go in this direction, that would be a reduction. Or if I go from a carboxylic acid to an aldehyde, that would be a reduction. So that's the concept. And these enzymes I wanted to bring up because these are non-CYP450 enzymes that are still under this broad umbrella of oxidation. So that's this part right here. Okay. And then a note on alcohol, or oxidation, with alcohols. This oxidation will only work if you have a primary or secondary alcohol. So this is a primary alcohol, and this is a secondary alcohol. And this central carbon, this carbon right here, needs to have at least one hydrogen on it for oxidation to happen. Because what is oxidation? Loss of hydrogen. So if I don't have hydrogen to begin with, I cannot do oxidation. So let me show you what I mean by that. If I put in a tertiary alcohol, right, this would be a tertiary alcohol. Let's compare all of these structures. Just to be clear, if you look at the primary alcohol, this carbon, this red carbon, is only bound to one carbon. That's what makes it a primary alcohol. Now, if you look at the red carbon in the second structure, it's bound to two carbons. That's what makes it a secondary alcohol. That red carbon in the third structure is bound to three carbons. That's what makes it a tertiary alcohol. So even if you see these alcohols in giant molecules with tons and tons of different things attached to it, you need to be able to recognize what is the carbon I'm interested in. I'm interested in the carbon that is directly bonded to my oxygen. In other words, I'm interested in this carbon that is directly bonded to my oxygen. That's the carbon I'm interested in. So that's the carbon that I need to see to look at to determine if it's a primary, secondary, or tertiary alcohol. Because if it's a tertiary alcohol, there's no way that you can undergo oxidation. So alcohol dehydrogenase would not be able to turn this tertiary alcohol into the next or the higher level oxidation state. That would not be able to occur. But primary and secondary, okay, so primary and secondary, you can do oxidation there. Okay. So here I can do oxidation, here I can do oxidation because this is a primary alcohol, this is a secondary alcohol. This tertiary alcohol cannot undergo oxidation because in order to have oxidation, you need at least one hydrogen on that carbon of interest. And if you see, before I ruin this molecule, if I redraw that tertiary alcohol, you'll see that there was no hydrogen attached to that carbon of interest. Right, so this carbon right here is actually attached to 3 different carbons, and so there is no hydrogen attached to that central carbon. There's no hydrogen right here. Whereas in this structure, we know that carbon's supposed to have 4 bonds, so there has to be 2 hydrogens there that are just not drawn out, and here there has to be 1 hydrogen that is not drawn out to make the 4 bonds. But here this carbon already has 4 bonds, so there is no hydrogen right there. So for that reason, this molecule cannot undergo oxidation. In the next video, we're going to go over nafcillin, which is one practice problem taken from Dr. Luo's practice problem sets. And we're going to go over the different metabolism pathways of nafcillin. And then we're going to do the same for butadiene, meclizine, and then APAP detoxification.